Our galaxy is moving through space at an incredible speed, and there's something pulling it. It's a kind of gravity anomaly, a modern mystery. It challenges a lot of what we assume. All the galaxies near us, they're all streaming toward one point, a single spot in the dark. There has to be something there, some immense source of gravity we can't see. It makes you reconsider your place. Your home isn't quite where you thought it was. The oldest light gave us the answer. Scientists went back to the beginning, to the echo of creation. That's the cosmic microwave background. It's a cold glow everywhere, the leftover heat from the Big Bang, cooled down over 14 billion years into microwaves. For cosmology, it's a map. It comes from everywhere at once, so it's a perfect frame of reference, like a still ocean. You can see any motion against it. And when they measured our motion against that backdrop, it was unsettling. Our whole local group of galaxies, the Milky Way and Andromeda, we're not drifting. We're racing. The speed was staggering, over 600 kilometers a second, more than 1,000,000 miles an hour. This was peculiar motion, a velocity so huge it couldn't come from the gravity of anything we could see. The big attractors we knew, the Virgo cluster, the Great Attractor, they were strong, but their combined strength fell short. The math didn't add up. Our neighborhood was being tugged by something far greater, something we could only see by the trail it left in our motion. That was the first concrete clue. Not in the stars, in the cold, uniform whisper of the universe's first dawn. That subtle imbalance is called the Dipole Anisotropy. It's a complex name for a simple idea. Imagine a dark room with one light on the ceiling. If you stand still, the light is even. But if you walk toward it, the light ahead gets a little brighter, a bit warmer on your face. And the light behind you feels a little dimmer, a touch cooler. You're moving through a still field of light, and your motion makes a gentle gradient. That's what they found in the cosmic microwave background. In one direction, that ancient light is slightly warmer. In the exact opposite direction, it's slightly cooler. The difference is tiny, about 1/1000%, but against the perfect uniformity of the early universe, it stands out. It's the Doppler effect across the whole sky. Like a siren's pitch rising as it comes toward you and falling as it goes away, the CMB light is blue-shifted to a higher temperature ahead of us and red-shifted to a lower temperature behind us. By measuring that tiny difference, they could do something remarkable. They could calculate our exact speed through space. The number was staggering. Our entire galactic neighborhood is moving at over 600 kilometers every second. That's like going from Earth to the Moon in about 10 minutes. This velocity was the first hard data point, the first real clue. And when they took that number and ran the equations backward, asking what gravity could give us that kind of speed, they hit a wall. All the visible matter we could see, all the galaxies and clusters nearby, their combined gravity wasn't nearly enough. It was like feeling a strong river current, but looking down and seeing only a shallow stream. The force was there, but the source was invisible. This discrepancy from that faint thermal whisper turned a curiosity into a full cosmic mystery. It meant our maps were wrong. Something huge was out there, pulling with the gravity of 100,000 galaxies, yet completely hidden from our telescopes. The search for the source of that pull, the hunt for what was moving us, had just begun. We had a direction, but not a destination. We knew we were moving, and we knew the speed. But to find what was pulling us, we needed a map of motion, not stars. That meant a new kind of census, a galactic survey on a scale that's hard to picture. Projects took on the task: the 2-micron all-sky survey, the 2-degree field galaxy redshift survey. For years, telescopes catalogued things. They recorded the positions of hundreds of thousands of galaxies and their motions. They measured the redshift of each one, that sign of its velocity. And when they plotted all that data, the universe did something. It began to flow. Those static points of light on a chart became a dynamic river system. Galaxies weren't just scattered, they were streaming. Like leaves in a gentle current, galaxy after galaxy drifted the same way, and we were in that current. Our entire local group, thousands of other galaxies, part of this immense cosmic flow. So the map gave the pull a face. It visualized that invisible force. All those streams, all those vectors of motion, they converged. They pointed like arrows toward one patch of sky near Centaurus and Hydra, a place with no remarkable bright galaxies, no dazzling quasars. Just a quiet, dark void, but the motion of everything around it told a different story. Something titanic was there. A gravity well so deep it was bending the paths of galaxies across hundreds of millions of light years. The surveys had done more than find a direction. They had drawn a treasure map with an X that marked a spot of profound emptiness. The mystery now had a location. The Great Attractor, that was the name for that quiet, dark void. It was the first real suspect. This region, about 150 to 250 million light-years away, it wasn't empty. It was a hidden overdensity, a huge concentration of mass, like a city hidden behind a dense fog. And that fog is our own Milky Way's plane, all that gas and dust and stars blocking our direct view. The Great Attractor sits right behind that. We couldn't see it with optical telescopes, but we could feel its pull. By tracking the motions of thousands of galaxies nearby, astronomers saw it. Those galaxies were all drifting toward that one point, their paths bent by gravity, which meant something massive was there. It was a key player, an anchor for our local galactic neighborhood. For a while, it seemed like the answer, but then the calculations got better and a problem came up. The Great Attractor was powerful, sure, but its gravity, as immense as it was, wasn't nearly enough. It could explain some of our motion, maybe a lot of it, but not all of it. Our local group was moving too fast with too much momentum. The numbers wouldn't balance. So the Great Attractor was a major force, but it wasn't the ultimate source. It was like finding a strong regional current, only to realize that current is part of a much bigger ocean gyre. Something even bigger was pulling on the Great Attractor itself. The hunt had to keep going further out. The search went further out into deeper space. And far past the Great Attractor, they found the anchor, the Shapley Supercluster. That name doesn't really capture it. It's the most massive concentration of galaxies we know of in our nearby universe. A huge metropolis of matter about 650 million light-years away. You could think of the Great Attractor as a major city. Then Shapley is the whole continent it's sitting on. It holds dozens of massive galaxy clusters. Each of those has thousands of galaxies, all bound in one immense gravitational web. The total mass is almost impossible to picture. If you could weigh it, it would be like 10,000 Milky Ways all pulling together. This structure is the dominant source of gravity in our entire cosmic neighborhood. Its pull is profound. It acts like an anchor point in the ocean of space, a gravitational center so powerful it draws everything toward it, our motion. The Great Attractor's motion, the flow of thousands of other galaxies, a lot of that traces back to the steady, patient tug of Shapley. For a while, it seemed like the mystery was solved. We'd found the primary engine behind the great flow. The invisible hand pulling us had a name and a location. But science, cosmology especially, rarely gives you a simple ending. Just like the Great Attractor wasn't the full story, the Shapley Supercluster, for all its immensity, presented a new puzzle. When they ran the most detailed calculations, adding up the pull of everything we could map, Virgo, the Great Attractor, Shapley itself, the numbers still came up short. There was still a portion of our speed, a significant part of that motion, over 600 kilometers per second, that was unexplained. the anchor was real. But the current was still stronger than it should be. Something was missing from the equation. The numbers weren't adding up, even with Shapley and the Great Attractor. Their huge gravitational pull, our speed was still too high. The math, based on the mass we could actually see in those places, gave us one predicted velocity, but the real measurement was much faster. There was a gap. A gravitational shortfall. It's like looking at a river with a strong current. You see a big dam upstream, and you think that explains the flow, but then you measure the water, and it's moving faster than that dam could possibly account for. So there has to be another source, something else further up, adding to the pull. That's where cosmology was. Either Shapley and the Great Attractor had way more mass than we thought, maybe hidden dark matter, or there was another player. Something even farther out, more massive, pulling on everything, pulling on Shapley itself. This wasn't just our motion anymore. It was the motion of our whole local sheet of galaxies. The discrepancy pointed to a deeper layer, a structure so large it orchestrates the flow of superclusters. The hunt for the source of the pull was moving from millions to billions of light years away. We've been looking at this the same way for a long time, thinking our motion has to come from something pulling us from ahead, a massive attractor, but gravity works both ways. It's not just what pulls you forward, it's also what isn't holding you back. So maybe part of our speed isn't a pull from the front, maybe it's a push from behind. That idea turns the whole question around, and it brings in this character, the Dipole Repeller. The name sounds like fiction, but the logic is just gravity. Think of a boat on a calm lake. A winch on the far shore pulls you, you move. That's the attractor, but imagine something else. Imagine the water draining away behind the boat. No pull from the front, but with less water holding you back, you drift forward. You're pushed by an absence. In space, these absences are voids, huge, sprawling regions that are almost empty. Very few galaxies, very little matter. Their gravitational pull is weak. So if you're near the edge of a giant void, things are unbalanced. All the normal matter and gravity is in one direction. The profound emptiness is in the other. You aren't so much pulled toward the mass, you're effectively pushed away from the void because there's nothing there to hold you. Research started to suggest that behind our local group of galaxies, opposite the Great Attractor and Shapley, there's one of these cosmic deserts. A region so underdense, so lacking in gravitational anchors that it adds to our motion. It's not creating a force, it's failing to provide a counterbalance. The collective gravity of all the mass in one half of our sky is competing with a staggering absence in the other half. So our motion, that 600 km/s journey, is probably the combined result of two colossal influences. The immense pull of the mass concentrations ahead of us, like Shapley, and the effective push from the vast emptiness behind us, the Dipole Repeller. It's a cosmic tug of war where one team barely shows up. This idea solves part of the number problem. It accounts for some of that unexplained velocity, but it also deepens the mystery. It means the structures governing our fate aren't just the bright clusters we can map. They're also the silent, dark voids between them. The emptiest places might be just as important as the most crowded. It's not just one force pulling us. It's a whole balance of pushes and pulls across the entire cosmic landscape. Our motion is part of something much larger, a bulk flow. Space isn't a static stage. On the largest scales, it's more like a vast, slow-moving fluid. And entire regions of that fluid can move together coherently in one direction. That's a bulk flow. It's the motion of a huge volume of space itself, carrying thousands of galaxies along. Our local group isn't swimming against the current. We're on a colossal cosmic conveyor belt. The engine of that belt is the combined gravitational gradient of everything around us. On one side, you have the immense concentrations of mass, the overdensities. The Shapley Supercluster is the prime example, a gravitational anchor pulling everything toward it. on the other side you have the profound emptiness. The underdensities, the dipole repeller and other voids, whose lack of gravity effectively gives us a nudge from behind. Our trajectory is the net result of this grand imbalance. We're sliding down a gentle slope in the fabric of space-time, a slope created by the hills and valleys of matter and emptiness. This explains why adding up individual attractors never gave the full answer. We're not being pulled by a single point, we're being carried by the flow of the entire structure. To truly understand where we're going, we can't just look at the bright spots on the map. We have to look at the map itself, the universe's large-scale structure as a whole. The pattern of filaments and voids, the cosmic web, dictates the currents. And our journey is just one small part of its immense, slow choreography. But the story doesn't stop with Shapley. There's a third clue, and it comes from looking at the most distant things we can see: galaxy clusters, billions of light years away. What they found was puzzling. When astronomers measured the motion of these ancient clusters, using the cosmic microwave background as a fixed point, they saw something strange. The clusters were moving, not in random directions but together in a stream, and that stream was aligned with the way we're moving locally. They called it dark flow. It was as if the whole visible universe was drifting on a scale that's almost impossible to grasp. This wasn't just our local group or our supercluster. This was a bulk flow of matter reaching out to the edge of the observable universe. The implication was staggering. If it's real, then the source of the pull isn't just a distant supercluster like Shapley. It has to be something even bigger, something whose gravity stretches across cosmic horizons, a structure so vast it can tug on clusters billions of light years apart. The most logical explanation, though it bends the mind, is that the source lies beyond what we can see, past the cosmic microwave background, in a region whose light hasn't reached us yet. A neighboring structure, a cosmic continent of galaxies so huge it makes Shapley look like an island. Its gravity would warp space-time on such a scale that it creates a current, affecting everything in our observable bubble. This idea is controversial. It challenges a cornerstone of cosmology, the cosmological principle. That principle says the universe should look roughly the same in every direction, on the largest scales, with no special place. A dark flow from an ultra-distant attractor would mean our observable universe isn't perfectly uniform. We'd be living on a gentle slope of a much larger landscape we can't see. The evidence for dark flow is still debated. Some later studies haven't confirmed it, but those initial findings remain a possibility. They suggest the ultimate answer to where we're going might not be on any map we can ever make. The true source of the pull could be hiding just over our horizon, in the darkness of the unobservable universe. That invisible structure is the whole mystery. Gravity is what pulls us, but most of the gravity out there comes from something we can't see: dark matter. It's the hidden framework. For every galaxy you can see, there's this huge, faint halo of the stuff around it, keeping it intact. And on the biggest scales, dark matter doesn't just surround galaxies. It builds the whole cosmic web. It makes these huge filaments and these massive nodes where clusters of galaxies collect. The structure of the universe is like a mountain range made of ice. The galaxies we see are just the very tops of the peaks, the part that catches the light. But underneath, holding all those peaks up, is this continent-sized foundation of solid rock. That foundation is dark matter, the gravitational pull we feel, the one pulling our whole galaxy, that's not mainly coming from the shining peaks. It's coming from the shape of that enormous, hidden bedrock. The great attractor, the Shapley Supercluster, these are the visible signs of enormous concentrations of dark matter. They're the deepest gravitational wells nearby, and like water going downhill, galaxies naturally drift into these wells. Our motion isn't some mystery of empty space pulling us. It's just what happens when you slide down the slope of a dark matter landscape that's hundreds of millions of light years wide. So the anomaly pulling us is really a map. But it's not a map of light, it's a map of shadow, a chart of where the dark matter is packed most densely. We're tracing the outline of this shadowy landscape by feeling its pull. Every measurement of our speed, every galaxy we see moving the same way, it's another data point. It helps us chart the invisible shape of the cosmos. That changes the question completely. We're not just looking for a missing object, we're trying to see the shape of the void and the hill, the push from the dipole repeller. That's a huge desert of dark matter, the pull toward Shapley, that's a mountain range of dark matter. Our journey is this slow descent from a sparse plane down into a dense, shadowy valley. And we're only starting to understand it. All this talk about pulls and pushes, sliding down dark matter slopes, that's happening inside a universe that's doing something else. The universe is expanding and it's accelerating. That acceleration comes from dark energy. It's the most dominant force now, a repulsive force right in the fabric of space, making galaxies rush apart. On the largest scales, dark energy is the counterforce. It works against gravity's pull. Gravity gathers matter. Dark energy pushes it apart. It stretches the cosmic web thinner over time. So there's this paradox, our local flow, this coherent motion of thousands of galaxies all moving together for hundreds of millions of light years. That's gravitational. It's the universe trying to collapse locally under its own weight, but it's happening inside a universe that's fundamentally trying to tear itself apart. Imagine walking steadily down a hallway while the floor itself is being stretched beneath your feet. The expansion is constant, a background force increasing the distances between everything. For a structure like our local flow to hold together, to keep all those galaxies moving together against that stretching, the gravitational pull behind it has to be exceptionally strong. It has to overcome not just the inertia, but the very expansion of space in that region. That makes the great flow and the anomaly behind it even more remarkable. It shows the raw power of gravity when matter clusters on such immense scales. The dark matter hills are so steep, the valleys so deep, they create a current powerful enough to persist. Inside an accelerating ocean, so we're caught between two cosmic tides. One is the ancient, attractive tide of gravity from the universe's hidden mass, pulling us toward the great attractors. The other is the modern, repulsive tide of dark energy, pushing everything apart. Our motion is direct evidence that here, in our local corner, for now, gravity is winning the tug of war. The invisible anomaly pulling us is so potent, it can carve out a river of galaxies in an expanding sea, mapping something you can't see. The true source of the pull is a landscape of dark matter, so we need to chart its hills and valleys directly. There's a cosmic trick of the light for that, a phenomenon called weak gravitational lensing. It works on a principle Einstein predicted. Massive objects warp the fabric of space-time around them. Light traveling through that warped space doesn't follow a straight line, it bends. A single huge mass, like a galaxy cluster, can act like a lens. It creates dramatic arcs and rings of distorted light from galaxies far behind it. That's strong lensing, but the effect is subtler and far more common on a grander scale. The vast, diffuse halos of dark matter that make up the cosmic web also warp space. Their gravity is immense, but it's spread out, so instead of creating spectacular rings, they impart a tiny, systematic distortion to the shapes of millions of distant background galaxies. Imagine looking through a vast, slightly warped window pane. The scene outside isn't broken, but every shape is subtly stretched just a little in a particular direction. That's weak gravitational lensing. By observing countless distant galaxies and meticulously measuring their shapes, astronomers can detect this coherent pattern of stretching. It's a statistical signal. No single galaxy shows it clearly, but across millions, the trend emerges. The direction and amount of the stretching tells a story. It reveals the presence and distribution of all the mass, visible and dark, that lies between those galaxies and us. This distortion is our tracer. It lets us draw a map of mass, not light. Upcoming missions are built for this very purpose. The Euclid Space Telescope and the Vera C. Rubin Observatory are designed to survey billions of galaxies across huge swaths of the sky. Their goal is to measure these tiny shape distortions with unprecedented precision. The result will be a three-dimensional mass map of the cosmos, a gravitational tomography scan of the universe. For our mystery, this is the key. These surveys will point toward that patch of sky near Centaurus and Hydra, toward the Great Attractor and beyond Shapley. They won't just see galaxies, they will weigh the emptiness and the fullness. They will measure the exact gravitational gradient of the dipole repeller void behind us and the true mass of the attractors ahead. They could reveal hidden superclusters, structures so enshrouded in dust or so distant they've remained invisible. Or they might confirm the profound depth of a void, showing us the true scale of the nothing that pushes. This is how we will finally see the shape of the pull, not by guessing from motion, but by directly imaging the gravity that causes it. The invisible anomaly will, for the first time, have its portrait drawn in the distorted light of a billion ancient suns. It's like having one detailed photograph of a huge landscape, but to understand what shaped it, you'd need to watch the whole thing form. So how do you see the universe grow up? You build one. That's where supercomputers come in. They run these cosmic time machines. The idea is simple. Start with a nearly uniform soup of matter and dark matter from just after the Big Bang. Apply the laws of physics, gravity, the expansion of space, dark matter's behavior, and then press play. Watch it unfold over 14 billion simulated years. The Millennium simulation is the famous one. It didn't just follow a few galaxies. It modeled over 10 billion particles, each a huge clump of dark matter, all interacting through gravity inside a virtual cube of space. That cube was over 2 billion light-years on a side. Running it took months on a supercomputer, and what came out of that digital soup was a revelation. A cosmic web, filaments of dark matter snaking through the void, meeting at dense nodes where thousands of galaxies would later gather, and between them, vast empty bubbles, the voids. The simulation didn't just produce a picture that looked right. It predicted the specific structures we'd later see. It showed how tiny quantum fluctuations in the early universe could, over eons, grow into the great walls and deserts we see now. For our mystery, these simulations are the test. Scientists can make thousands of virtual universes, each with slightly different starting conditions or rules. They put a virtual observer inside, one that mimics our position in the Milky Way, and fast forward. They watch how the virtual galaxies flow. Do they stream toward one point? Does a great attractor and a dipole repeller naturally appear in the gravity map? The power is in comparison. Run the simulations, then compare the predicted bulk flows to our actual measured motion. Cosmologists can perform a kind of cosmic autopsy. They can ask, does our observed velocity fit what's typical in a universe with our standard models of dark matter and dark energy? Or is it an outlier, a statistical anomaly that means something's missing? So far, the simulations suggest our motion, while on the high end, isn't impossible in the standard model. They show that structures as massive as the Shapley Supercluster, combined with the emptiness of a nearby void, can generate flows of the size we see. But the match isn't perfect. The precise direction and speed sometimes hint that our local sheet of galaxies might be tugged by an even larger, more distant mass. Something the biggest simulations are only starting to hint at. In a real sense, these digital universes are our guides. They let us rewind the tape of cosmic history. Not just to see where we came from, but to test the invisible forces pulling us right now into the future. The universe isn't just random lights, it has a structure. A real architecture. We call it the cosmic web. Think of it like froth on a dark ocean or a spider web, a three-dimensional one spanning billions of light years. Where the threads of that web cross, you get bright knots. Those are galaxy clusters, cities of 1,000 suns. The threads themselves are filaments. Long rivers of galaxies and dark matter, and between the threads, the huge empty spaces. Those are the voids, cosmic deserts. That's the true large-scale structure of everything. And we're part of it, the Milky Way, Andromeda, our local group. We're not in some average, empty place. We're almost certainly inside one of these filaments. We're a strand in the web, and our motion, that journey toward the unseen thing, it makes sense in this model. We're not being pulled by one point, we're flowing. Our entire filament, this river of galaxies we're in, it's streaming downhill, down the gravitational landscape of the web. We're following the curve of space-time toward a node. A junction where multiple filaments come together. That junction is a place of immense density, immense gravity, a supercluster of superclusters. The direction of our pull toward Centaurus and Hydra, it points right to one of these nodes. It's the gravitational heart of our entire local sector of the web. So the mystery of the pull, it becomes a question of geography. We're not lost, we're precisely located. Our home filament is just caught in the current, sliding along the invisible contours of the cosmic web toward its nearest great gathering place that changes the scale of the story again. It's not just our galaxy being pulled, it's our entire local strand of the universe's structure, moving in concert with the grand design. Look toward the southern sky on a clear night. If you're far enough south, you can see two constellations, Centaurus, the centaur, and Hydra, the water serpent. To your eye, they're just patterns. Old stories written in the stars, but if you could draw a line from Earth through that part of the sky, you wouldn't be pointing at a star. You'd be aiming into a deep emptiness. That line of sight is our direction. It's the way everything around here is moving. When you point a telescope there, you're doing something. You're not just looking at stars. You're looking along the path of a river, a cosmic river. Your gaze goes right through the crowded plain of our own galaxy. You see the star fields, the nebulae, all the landmarks of home. And then you push past them into the void between galaxies, and out there in that specific slice are the markers. The first big stop is the Norma cluster. A dense gathering of galaxies about 200 million light-years away. It's part of what they call the Great Attractor region. Further out, your line of sight reaches the Shapley Supercluster. That huge metropolis of mass, but the direction itself, those coordinates near Centaurus and Hydra, it's more than a location now. It's an answer. It's the solution to a very old puzzle. The question of which way we're going. Every measurement of galaxy motion points there. Every subtle distortion in the cosmic background radiation. Every supercomputer simulation of dark matter. They all converge on this one patch of darkness. It's a quiet spot. No bright star marks it for the naked eye, but it holds the gravitational address. The address of the most influential structure in our neighborhood. So next time you see those constellations, remember, you're not just seeing mythology. You're looking at the destination for our entire galactic journey, a point in the void that pulls with the force of 100,000 galaxies. Our picture of a moving, changing universe is actually very new. For most of human history, the stars were fixed. They were just a perfect, unmoving background, and the planets were the only things that wandered. That static universe was the idea, really, all the way into the 1900s. So when astronomers first looked at the light from distant nebulae, they expected to see randomness. But they didn't. They saw a pattern, and it was consistent. Almost every galaxy's light was shifted toward red, and the more distant the galaxy, the bigger that redshift became. Edwin Hubble, using Henrietta Leavitt's method for measuring distances with stars, put it together. That redshift wasn't from galaxies moving sideways through space. It was from space itself stretching. The universe wasn't static. It was expanding, carrying galaxies apart, like raisins in dough as it rises. That changed everything. It meant the cosmos had a history. It had a beginning and it had a direction. But this discovery of the overall expansion created its own assumption, that galaxies were just passive, riding that expanding fabric of space-time, drifting apart in a perfectly smooth, uniform flow. They called it the Hubble flow, and for a while it seemed elegantly simple. You could explain any galaxy's motion with that one cosmic river, carrying everything away from everything else. Then the measurements improved, and when astronomers looked at our closest galactic neighbor, Andromeda, they found something wrong. Andromeda isn't redshifted. It's blue-shifted. It's moving toward us on a path to collide billions of years from now. That was the first big clue. The Hubble flow wasn't the complete picture. Galaxies had their own individual motions laid on top of the grand expansion. These are called peculiar velocities. They're the deviations, the local ripples and currents inside the great river. Our Milky Way has one. Andromeda has one. Every galaxy does. They're caused by local gravitational pulls, the tug of a nearby cluster, the push from a neighboring void. Finding these peculiar velocities broke the last idea of a perfectly uniform cosmos. It meant if you could subtract the smooth, predictable expansion of space, you'd find a hidden landscape of motion underneath. A landscape where galaxies stream and cluster, pulled by the invisible geography of mass. That realization was the essential first step. It turned astronomers from map-makers of static positions into detectives of dynamic flow. They started asking not just where a galaxy is, but where it's going. And when they began to map those peculiar velocities across thousands of galaxies, a pattern showed up. They weren't random, they were coherent, they pointed. That was the birth of the mystery, finding that our local flow is a real, physical current within the expanding universe, a current that leads straight back to the question of what, out there in the dark, has that much gravitational pull. 600 kilometers per second. That's the speed, our whole local group of galaxies moving against the oldest light we can see. To even think about that number, you have to leave behind what we know on Earth. A jet goes about 1 kilometer per second. The Parker Solar Probe, when it's diving toward the Sun, hits 200. We're going 3 times that. So the distance from Earth to the Moon, that takes us about 10 minutes. Earth to the Sun, less than 3 days. This isn't drifting. It's a full rush straight through, and it's not just our galaxy. It's dozens of them, trillions of stars all moving together, this shared momentum. The force to make that happen is hard to picture. You can't just push a galaxy. They're massive. They resist. To get so many moving in the same direction, to accelerate all that mass to this speed, the gravity behind it has to be enormous. It's the clearest sign our part of space isn't balanced. We're in a current flowing down a slope so steep it bends the motion of everything for hundreds of millions of light years. That number 600, it's not just a measurement. It's a direct readout of the anomaly's strength. It tells you how deep the well is we're falling into and how empty the place is we're leaving. Every calculation starts there, that velocity. Every theory, every map, every simulation has to account for it. It's the fixed point. To see what's pulling us, you have to look right through the center of your own home. That's the problem, the direction we're all moving, toward the great attractor, toward Shapley. It's right behind the brightest, thickest part of the Milky Way. Our own galaxy blocks the view. Astronomers call it the Zone of Avoidance. It's this broad band across the sky where the disk of our galaxy, with all its stars and gas and dust, just obscures everything behind it. Like trying to see distant mountains through the skyline of your own city. the thing that defines our neighborhood ends up hiding the biggest landmark beyond it. For decades, that zone was a blind spot on the map. The Great Attractor was in that blind spot, a gravitational phantom. We could feel the pull, but we couldn't see it. What it actually was, the galaxies that must be there, were veiled by our own galactic backyard. To solve the mystery, we had to find a way to see through. That meant looking with different eyes. Optical light, what our eyes see, gets scattered and absorbed by all that dust, but longer wavelengths can pass through. Infrared light, for instance, slips between the dust grains. Space telescopes like the Infrared Astronomical Satellite, later WISE, they scanned the Zone of Avoidance. They weren't seeing starlight. They were seeing the gentle heat glow of dust-obscured galaxies in the infrared. Slowly, a hidden population emerged. Entire galaxies, once invisible, got mapped. But infrared is just one window. Another tool is radio astronomy. Hydrogen gas, the most common element, emits a faint radio signal at a specific frequency. A signature that cuts through dust. Surveys like the H.I. Park's All-Sky Survey used giant radio dishes to listen for that whisper across the zone. They weren't looking for light. They were tuning in to the cold hydrogen gas inside galaxies. By detecting that radio hum, they could pinpoint the location, the distance, the motion of galaxies completely hidden to optical scopes. Like using sonar to map a sunken ship in murky water, layer by layer, wavelength by wavelength, the blank space on the map filled in. The Great Attractor began to take shape. Not as one object, but as a complex tapestry of galaxy clusters and filaments, all lying in that obscured zone. The work is painstaking, it's ongoing. Every new survey reveals more of the hidden architecture. It's a reminder. The universe's biggest secrets are often hidden in plain sight, masked by the glare of what's closest to us. To understand the distant pull, we first had to learn to see through ourselves. These maps we have now, they're just the first sketches. The real portrait of the cosmic web, the source of that pull, is being painted by a new generation of telescopes. Two missions in particular, the European Space Agency's Euclid Telescope and NASA's Nancy Grace Roman Space Telescope, they're not like Hubble, which looked deeply at tiny, beautiful patches of sky. These are surveyors. Their job is to stare at enormous swaths of the cosmos methodically for years. Euclid launched in 2023, and Roman is set to follow later this decade. Together, they'll perform a census on a staggering scale. Euclid aims to measure the shapes and positions of over 1 billion galaxies. Roman will image thousands of times the area of the full moon in a single shot, building a panoramic view of the universe's history. But they're not just taking pictures, they're performing a grand cosmic measurement. Each galaxy's redshift gives its distance, building a three-dimensional model of the universe. And each galaxy's subtly distorted shape, that signature of weak gravitational lensing, tells us about all the dark matter its light passed through. Imagine having a blurry, low-resolution map of a mountain range, and then suddenly receiving a satellite image so detailed you can see every contour line, every gully, every rock. That's the leap these telescopes promise. They will create a mass map of the cosmos. For the first time, we won't just infer the dark matter hills and valleys from the motion of galaxies. We will see their direct gravitational imprint, etched into the light of 1 billion ancient suns. This data will be poured into supercomputers, refining our simulations to an uncanny degree of accuracy. It will let us weigh the Great Attractor and the Shapley Supercluster with precision, measuring their true gravitational might. It will map the exact boundaries and depth of the dipole repeller void, quantifying its effective push. And it might reveal entirely new structures, hidden masses or profound emptinesses that our current, coarser maps have completely missed. The direction of our motion, that line toward Centaurus, will be scrutinized like never before. Every pixel in that vast sky survey will contain information about the gravitational gradient we are sliding down. These missions are building the ultimate gravitational compass. They won't just tell us where we're going, they will show us the shape of the slope itself, finally making the invisible anomaly visible. That coherent flow over such an immense distance, it raises a deeper question. It touches one of the most fundamental ideas in cosmology, a guiding principle for a century, the cosmological principle. It states, in simple terms, that on the largest scales, the universe is homogeneous and isotropic. Homogeneous means it's roughly the same everywhere, no special place. Isotropic means it looks the same in every direction, no special direction. The idea is, if you step back far enough, the cosmos is a uniform soup, galaxies sprinkled evenly throughout. This principle isn't just philosophy, it's the bedrock. It lets us apply the laws of physics consistently across the cosmos. It lets us believe what we see from our vantage point is representative of the whole. But our motion, this dark flow some have detected, it presents a quiet challenge. A flow that coherent over billions of light years, it suggests something. It hints the universe might not be perfectly smooth on those grand scales. It might be lumpier. Think of it like floating in what you believe is a perfectly calm, infinite ocean. You expect no current, just gentle, random waves, but then you drop a dye marker, you watch. Instead of diffusing randomly, the dye begins to stream in one specific direction. And you notice other driftwood, other debris, all moving the same way as far as you can see. That organized motion tells you the ocean isn't featureless. There's a continental slope somewhere, a deep trench, a massive underwater ridge, creating a basin-wide current you couldn't see from the surface. Our great flow is that dye marker. It suggests the distribution of mass dark matter. Galaxies might have structures so vast they create gravitational gradients on scales we thought were too large for such variations. These would be continent-sized features in the cosmic web, making the universe anisotropic, directionally different, on scales exceeding 1 billion light-years. This isn't to say the cosmological principle is wrong, but it might need refinement. Perhaps it only truly applies on scales even larger than we've probed. Or perhaps our local volume of the universe, enormous to us, is just one slightly unusual bubble in a vaster, smoother whole. The mystery of the pull forces this confrontation. Are we living in an average neighborhood, or are we in a slightly special place, on the slope of one of the universe's largest hills? The answer reshapes our map and our entire cosmic context. It asks whether the forces guiding our galaxy's journey are a local phenomenon or a sign of a grander, more textured architecture we are only beginning to sense. Our destination is a collision, but on a cosmic timescale. The gravity pulling us is patient, relentless. Over billions of years, the current carrying our local group guides us toward the great masses ahead. We're not headed for a direct impact with the Shapley Supercluster. That's too distant, expansion keeps it out of reach. But we are destined to merge with the larger structure we're part of. Our filament of the cosmic web, with all its galaxies, flows toward a node, a gravitational meeting point. In the far future, our local group, long since merged into one elliptical galaxy from the Milky Way and Andromeda collision, will combine with other groups in our filament. We become part of a new, immense galaxy cluster, a city of stars in an ever-darkening universe. That's the gravitational fate. Local flows continue, gathering matter into these vast, isolated islands. But there's a counterforce, dark energy, the mysterious energy causing expansion to accelerate. On the largest scales, it's the dominant player. As eons pass, its influence grows. While gravity wins locally, binding galaxies into clusters, dark energy wins globally, pushing those clusters apart. Imagine our future mega-cluster, this island of 1 trillion stars. Around it, the void deepens. The space between our cluster and all others stretches faster. light from other structures redshifts into invisibility. The sky for any future civilization there grows profoundly dark. They see only the stars of their own gravitationally bound island, adrift in an infinite black ocean. The great flows we measure today, the currents defining our motion, will one day cease to exist. Not because they stop, but because their destinations, the other clusters, are carried beyond the cosmic horizon by expansion. The pull becomes irrelevant, its source forever lost. So the journey has two endings, one local, one universal. Locally, we head for a grand merger, a gathering into light dictated by the invisible hills of dark matter. Universally, we head for isolation, a quiet drifting apart dictated by the repulsive energy of empty space itself. Our present motion is a snapshot of this brief, dynamic era. A moment where gravity and dark energy are still in contest for the shape of our neighborhood. We live in the time of the flow, able to measure the pull and trace its source. That won't always be true. In a future so distant it defies comprehension, the anomaly that pulls us will be a memory, its evidence stretched away into nothing. The story, then, isn't just about where we're going. It's about witnessing the architecture of the universe during the singular era, when its two most fundamental forces can both be seen at work. But what if the invisible landscape just isn't there? That's the other possibility. Maybe the anomaly pulling us isn't hidden mass. Maybe our understanding of gravity is wrong. That idea leads to a radical alternative, a different physics. It's called modified Newtonian dynamics, MND. The core idea is simple and it flips everything. Maybe there's no dark matter. Instead, the laws of gravity, Newton's, even Einstein's, might change subtly in places where the force is extremely weak. Like the vast spaces between galaxies, in our solar system where gravity is strong, Newton and Einstein work perfectly. They predict planetary orbits with stunning accuracy. But out in the outskirts of a galaxy, where the gravitational pull from the center becomes incredibly faint, MND says the force of gravity doesn't fade away as quickly. It gets a tiny, persistent boost. That small change in the math has a huge effect. It can explain why stars at the edges of spiral galaxies orbit just as fast as those near the center. The thing we attribute to dark matter halos, for the great flow, the coherent motion of thousands of galaxies, MND offers a different interpretation. Proponents suggest the immense pull we feel might not be from a hidden supercluster. It could be a natural consequence of modified gravity acting across those colossal distances. In this view, the universe's large-scale structure, the filaments and voids, would form differently. The flows would emerge from the modified equations themselves. Without needing an invisible scaffolding of dark matter to hold it all up, it's a profound shift. Instead of mapping an unseen world of dark matter, we'd be charting the true, nuanced shape of gravity's reach. The mystery of the pull becomes a laboratory for testing the fundamental rules. Could the force that holds our feet to the ground behave differently in the profound emptiness between galaxy clusters? The evidence so far is mixed. MND successfully explains many galaxy rotation curves, but it struggles with other observations, like the behavior of colliding galaxy clusters, where visible matter and gravitational effects seem to separate. That's a strong point for dark matter. The great cosmic flow is another key test. We need detailed simulations of a MND universe to see if it can naturally produce a bulk motion as large and coherent as the one we observe. The debate isn't settled. It's a fork in the road. Down one path, a universe filled with invisible, mysterious particles that shape everything. Down the other, a universe where the force we think we know has hidden depths. Revealing itself only on the grandest stages, both paths explain the same fact. Something is moving us, whether that something is a hidden continent of shadow matter or a subtle rewrite of gravity's oldest rules. The journey to find out reshapes our place. There's one last possibility. It's so speculative it kind of redefines what a mystery even is. Could the source of this pull be outside our universe entirely? In theoretical cosmology, there's this mind-bending idea, the multiverse. The idea that our universe, with all its galaxies and dark energy, is just one bubble. In a kind of frothing, infinite cosmic foam, each bubble is a separate universe, with its own laws, its own physics, its own beginning. They're thought to be forever separate, expanding away from each other in a higher dimensional space we can't perceive. But what if they aren't perfectly isolated? Some highly speculative models suggest these bubble universes, while not touching, could still exert a subtle gravitational influence on one another. Through the fabric of whatever lies between them, their immense masses, their entire cosmic landscapes, could create gentle gravitational tides in the space that contains them. Think of two soap bubbles floating close together in a still room. They don't pop, they don't merge, but their surfaces might deform slightly, each feeling the faint presence of the other. In that scenario, the great flow we're part of, that coherent motion of thousands of galaxies, might not be caused by anything inside our bubble at all. It could be a cosmic slope created by the gravity of a neighboring universe, a titanic island just over the horizon of everything we can observe. That would be the ultimate invisible anomaly. Not dark matter, not a void, but an entire other cosmos pulling on ours from beyond the veil of reality itself. The direction we're moving, that line toward Centaurus, would then be a compass needle, pointing not to a place in our sky, but to a location in a space we can't even fathom. It's a staggering thought. It pushes the mystery from a question of what's out there in the dark to what's out there beyond the dark. Now, this idea is purely theoretical. There's no direct evidence for a multiverse, let alone for gravitational leakage between them. For now, it's a fascinating thought experiment. A testament to how deeply this anomaly challenges us. It shows that when the data points to something unseen, science has to follow the trail, no matter how strange it gets. Whether the pull comes from dark matter hills, a rewrite of gravity, or a whisper from another reality, the journey to understand it keeps redefining our place in the grand scheme of everything. This pull toward the dark, it's always been more than just a scientific question. It has its own weight in how we think. Long before we had the surveys or the maps, this idea of a hidden force guiding everything, it connected to something. These cosmic mysteries, with names like the Great Attractor or the Dark Flow, they've given stories a place to grow. In novels and films, it becomes a beacon, or a hidden civilization, or a tear in space pulling us toward something we can't see. Those stories, they touch on a basic need, the need for a destination. The idea of just drifting forever, it makes us uneasy. We want a center, we want the motion to have a point. Science gives us the numbers, the velocities. But stories, they give it meaning. They turn a statistical oddity into a step in a much larger journey. Documentaries and science shows, they focus on this. They frame it as the big unsolved mystery. The visuals are strong arrows on a map of stars, all pointing to one dark spot. It makes the unknown visible in a way data alone can't. This resonance, it's an old feeling. It's in the old myths from everywhere, the voyage to the underworld, the journey to the world's axis, the magnetic mountain pulling ships. These were all attempts to explain a direction they felt in the cosmos. Our ancestors watched the turning stars and saw intention. We watch the streaming galaxies and see a pattern. The scientific search for the source in a deep way, it's just the newest version of that old storytelling. We're still trying to chart the unseen forces that guide us. We just traded constellations for superclusters. We traded gods for halos of dark matter. The anomaly pulls us through space, but also through the ways we try to understand our place in it. This cultural footprint, it shows the mystery is still alive. It lives in the space between the equations on a board and the feeling you get looking up at the sky. wondering if we're all moving toward the same unseen shore. The cosmic microwave background isn't just a static map. It can also detect motion. There's a subtle phenomenon called the kinematic Sunyaev-Zeldovich effect. It uses that ancient light as a kind of cosmic speedometer. The principle is intricate. The cold photons from the CMB travel across the universe. Sometimes they pass through these vast, hot clouds of gas. The gas surrounds galaxy clusters. It's so energetic it can scatter the CMB photons. It gives them a tiny kick, and if the galaxy cluster itself is moving, that motion leaves a specific signature on the scattered light. It creates a minute temperature shift, a faint hot spot or cold spot in the CMB, in the cluster's direction. It depends on whether the cluster is moving toward us or away. The shift is incredibly tiny, just a few millionths of a degree, but by measuring this effect across hundreds of clusters, astronomers can do something. They can reconstruct the bulk flow, that's the large-scale streaming motion of matter, and they do it entirely independently of galaxy redshifts. It's a completely different line of evidence. The results are telling. Studies using this technique have detected coherent flows on scales of hundreds of millions of light years. The motion they trace aligns with the direction we already know. Toward that patch of sky near Centaurus, it confirms the flow isn't an artifact. It's not just how we measure galaxy motions. It's a real, physical current in the cosmos. It's felt even by the hot gas between galaxies. This independent verification strengthens the case. The anomaly isn't just pulling stars and galaxies. It's moving entire atmospheres of million-degree gas. The kinematic Sunyaev-Zeldovich effect gives us a new tool to weigh the pull. You compare the strength of the flows it measures to predictions. Predictions from our maps of visible mass, that gives another estimate of what's missing. And once again, the numbers suggest the visible structures aren't enough. The gravitational engine behind the flow must be more powerful or more distant than our current catalogs show. It's like feeling the wind on your face. You confirm its direction with a weather vane, only to realize the breeze is stronger than any storm on your horizon should produce. The search for the source now has multiple witnesses. They're all telling the same story, a story of an unseen, commanding presence in the cosmic dark. We're not the only current out here. There are other great flows, distant rivers of galaxies, all moving together across billions of light years. They're like siblings to our own motion. They show this isn't just our mystery. It's something the universe does. In one direction, a survey of more than 400 galaxy clusters found a coherent stream. These immense structures drifting together against the expansion. In another region, a different study saw a similar pattern, a slow river of galaxies guided by something unseen. Each of these flows is a signature. They're the visible traces of the cosmic web in motion, the slow drainage of matter out of the voids into the filaments and nodes. Gravity's patient work, sculpting the universe over eons. These flows tell us that what we see locally isn't an oddity. It's the standard condition, a universe still gathering itself into shape. Galaxies aren't static islands. They're passengers, riding the gentle gravitational waves from the hills and valleys of dark matter. Every bulk flow ours included is a chapter in the same story. How a nearly smooth early universe became the intricate, webbed structure we see now. And it's a process that's still going, gravity writing the next lines in the dark. The Planck satellite was out there, 1 million miles from Earth. It was listening, measuring the cosmic microwave background, that ancient light, with a precision we'd never had before. For 4 years it gathered data, building a map, every fluctuation, every tiny temperature difference. When the scientists processed it all, they went back to the dipole. That sign of our motion, Planck's data was so clean, it let them measure our velocity against that primordial backdrop with a new accuracy. The number was confirmed, refined. Our speed, measured against the echo of the Big Bang, was over 360 kilometers per second. That was the seventh clue, and maybe the most grounding one. Because Planck's precision did something crucial. It set firm boundaries. It helped rule out some of the more exotic possibilities for this flow. It showed the motion was real, significant, but not as extreme as some early measurements had hinted. There was no need for radically new physics, at least not from this alone. The flow fit within the margins of what might be possible in our standard model, with dark matter and dark energy. But here's the thing, by narrowing the possibilities, Planck actually deepened the mystery in a new way. It grounded the anomaly in robust data. This wasn't speculation. It was measurement. The satellite told us with confidence that we are moving at a specific speed in a specific direction, and then it handed the puzzle back. Those refined numbers became a new target for simulations. Could our best models of cosmic structure, using all the visible matter and dark matter we know about, produce a bulk flow exactly this strong, exactly this way? The answer often was not quite. The models came close, but the match wasn't perfect. So Planck's precision acted like a high-powered microscope. It didn't make the strange shape disappear. It revealed its edges more sharply, showing us exactly where our understanding might still be incomplete. The satellite transformed the great flow from a curious anomaly into a precise instrument, a ruler to test our maps of the invisible universe. Its legacy is a kind of paradox. By confirming the reality of the motion and ruling out the wildest theories, it made the hunt for a conventional explanation even more urgent. And in some ways, even more challenging. Our galaxy is a leaf in a current so vast we can't feel it moving. The forces that shape our path, they operate on a scale that just defies intuition. To understand what 600 kilometers per second means for something 100,000 light years across, you need a different measure. Think of the Pacific Ocean. Its deepest currents, they move with a slow, planetary purpose, carrying volumes of water you can't really imagine. A single leaf floating on the surface near Japan, it would have no sense it was part of the Kuroshio current. It wouldn't know this flow travels thousands of miles, that it shapes climates, steers storms, connects continents. The leaf just moves. It responds to forces it can't see and can't comprehend. That's our position. The Milky Way, with all its hundreds of billions of stars, is that leaf. The great flow is that current, and the dark matter, the hills and the voids, those are the hidden continents and trenches below. Shaping everything, we measure the speed, we chart the direction, but the sheer size of the machinery moving us, that's what humbles you. The slope we're sliding down, it was built over billions of years. By the collective gravity of structures millions of light years apart, all of human history, from the first tool to the latest telescope, it's all unfolded while we traveled a fraction of a single pixel on this map. This perspective, it's the final gift of the mystery. It's not just about finding what pulls us, it's about recognizing a truth. We live inside a dynamic, structured universe. One where the smallest particle and the largest supercluster are woven into the same gravitational tapestry. Our journey reminds us, to understand our place, we have to look beyond our home. Beyond our local group, even beyond what we can see. We have to learn to read the universe by the currents it creates, the currents in the dark. This grand flow isn't just something happening far away. It actually affects the science we do right here in our own galaxy. To understand the universe correctly, astrophysicists have to subtract our own motion first. It's like trying to measure a river's current while you're standing on a moving boat. If you don't account for the boat's drift, your measurements of the water will be wrong. Our galaxy's journey at 600 kilometers per second is that drift, and it directly impacts one of cosmology's most important numbers, the Hubble constant. That constant tells us how fast the universe is expanding right now. To measure it, astronomers look at distant galaxies. They measure their redshift, calculate how fast they're moving away from us. But our own motion through space, our peculiar velocity, adds a small, systematic shift to those measurements. For a galaxy in the direction we're heading, its light is a little extra redshifted because we're moving toward it. For a galaxy behind us, it's the opposite. If you don't correct for this, your map of universal expansion gets slightly warped. It's a subtle effect. But in a field where scientists are arguing over discrepancies of just a few percent, it's absolutely critical. This invisible pull shapes how we see the expansion of everything. And the influence reaches even closer to home, into the structure of the Milky Way itself. Astronomers mapping the precise orbits of stars around our galactic center have to account for this flow. Our entire galaxy is moving, which means the frame of reference for measuring stellar motions is itself in motion. It's a bit like trying to chart the flight paths of bees inside a hive that's being carried on the back of a truck. The bees have their own intricate patterns, but superimposed on all of them is the larger motion of the vehicle. To understand the bee's true behavior, you have to know the truck's speed and direction first. Similarly, to build an accurate model of the Milky Way's gravity, its dark matter halo, its history, we have to subtract the peculiar velocity of the entire galaxy. This local anomaly, born from structures hundreds of millions of light-years away, quietly adjusts the calculations for stars just thousands of light-years from Earth. It connects the immense to the intimate. It shows that no observation in our universe is truly isolated. The great flow is a lens, and only by understanding its distortion can we hope to see the cosmos clearly. We do this thing, we map a pull we can't feel, a current across a billion light-years, and it asks something of us. Why? We have immediate needs, but we dedicate this effort. We won't use the great attractor for power. It won't cure illness. It won't grow food. Its value is different. It answers a need to understand the context of our existence. Where we came from, where we are going on the grandest scale, it's the same drive, the first astronomers charting stars, not just for navigation, to find a pattern. We are a species that builds stories. Science is our most rigorous storytelling. It's how we test the myths, replace speculation with evidence, uncover the true narrative. Slowly, this mystery, the invisible pull, is a chapter. By tracing its source, we read the history of the universe's structure. We learn how the ripples of the Big Bang grew into the vast architecture that guides our path now. Each telescope pointed at that dark patch in Centaurus, each supercomputer simulation of dark matter. It's an act of cosmic archaeology. We are digging through time and space to uncover the foundations of everything we see, the resources, the engineers, the scientists, the years. They are not spent on an abstract puzzle. It's an investment in self-knowledge to comprehend the forces that move us, to better comprehend our own place. It moves us from being passive inhabitants to active participants in understanding. This journey answers a quiet question. The night sky whispers it. What is this place we call home? What unseen hands shaped its destiny? The search for the source of the pull. It's a search for our own cosmic address. We have a map, but the territory itself is still hidden. We've been searching for decades, and the same basic questions still drive every new observation. What is the exact distribution of mass that's pulling us forward and pushing us from behind? We know the major anchors, the great attractor, the Shapley Supercluster. And we know the profound void, the dipole repeller. But the precise gravitational weight of each one, the exact shape of their dark matter halos, whether there are even larger, more distant structures involved, all of that is still being measured. The numbers are close, but they're not perfect, and that gap between prediction and observation is where the mystery lies. Then there's the idea of dark flow. This coherent motion of galaxy clusters across billions of light years. Is it a real phenomenon or just a statistical mirage? If it's confirmed, it would be monumental. It would suggest the source of the pull lies beyond our observable horizon, in a neighboring universe of staggering scale. If it's refuted, that grounds us back in our local cosmic web. But it still leaves the strength of our flow needing an explanation. The debate is active. Papers are published on both sides. It shows how carefully this data is being scrutinized. And under all of this is the most profound question of mechanism. Can all of this be explained by the standard model of cosmology, with its dark matter and dark energy? Or does the persistence of these flows hint that our theory of gravity itself needs revision, like modified Newtonian dynamics proposes? Each camp looks at the same sky and sees something different. One sees an invisible landscape of unknown particles. The other sees a fundamental force behaving in unexpected ways in the deep quiet between galaxies. This isn't a settled story in a textbook. It's a live investigation. Astronomers and physicists are actively debating, simulating, observing. The field is poised on the edge of new revelation. Upcoming data from the Euclid and Roman space telescopes will give us a gravitational map of unprecedented detail. It could weigh the void and the supercluster with finality. New surveys will scan the zone of avoidance with more sensitive eyes, maybe revealing hidden giants. Each new data release could, at any moment, tip the scales toward one explanation and away from another. We're witnesses to a discovery in progress. We're watching the outline of an invisible continent slowly come into focus, one pixel of distorted starlight at a time. This cosmic pull, it's not something only astronomers are tracking. It's happening out in the open. You can follow it. This is one of the big open questions in science right now, and the data is out there. A lot of the galaxy surveys that map this flow, like the Sloan Digital Sky Survey, they release their findings publicly. You can go online, pull up these interactive sky maps, and see for yourself. Millions of galaxies, their positions, their motions, all pointing toward something, and those aren't just images, that's the raw evidence. It's the current we're caught in. You can even take part. There are citizen science projects that ask the public to help classify galaxies from these huge surveys. You lend your eyes, your curiosity, and you're helping build the maps that trace the large-scale structure of the universe. Every galaxy you identify becomes another data point. It adds to how we see the cosmic web, the gravitational forces shaping it. It's a way to be part of the discovery. To have a hand in charting this invisible landscape that's guiding our galaxy's path. And to stay current, you can follow the institutions driving this. NASA, the European Space Agency, they publish new findings from missions like Euclid, the Roman Space Telescope. Journals, their public websites, they offer summaries of new papers on bulk flows, dark matter mapping. The conversation is happening now, in press releases, science news, conference announcements. The next big clue could come tomorrow, and that changes the experience. You're not just hearing about a distant anomaly. You can watch the evidence build in real time, see new gravitational lensing maps when they're published. Read the debates about dark flow in scientific discussions. This search for the source of the pull, it's a living endeavor. Its door is open. It invites anyone who looks up at the night sky with wonder to come inside. To follow the trail of data, to witness as we slowly, collectively bring the invisible into view. The cosmic microwave background gave us our first clue. That faint temperature difference, the dipole anisotropy, it told us our speed, our direction. We were moving against the cosmic backdrop. That measurement sent us to the galaxy surveys. And those maps showed a river, not random drift but a coherent flow. Thousands of galaxies, our own included, all streaming toward a specific, dark patch of sky. That river led to the Great Attractor, a hidden concentration of mass veiled by our own galaxy's dust, a major landmark but not the only source. Following the current further, we found the true anchor. The Shapley Supercluster, a continent of galaxies. Its immense pull orchestrates the motion of our entire local universe. But even Shapley's gravity left some of our speed unexplained. The answer to that came from looking the other way, toward the Dipole Repeller, a vast, underdense void. Its profound emptiness fails to hold us back, so it gives us a nudge forward. Underpinning all of this is dark matter. It provides the slopes and valleys. Its distribution, mapped through weak lensing and simulated in supercomputers, creates the cosmic web. And within that web, our local filament of galaxies is sliding down a gentle slope. The consensus now is a symphony of these forces. We're carried by a bulk flow. The net result of the immense pull from mass concentrations ahead, like Shapley, combined with the effective push from the staggering emptiness behind. It's a dynamic balance, attraction and absence, sculpted by dark matter, set against the accelerating expansion from dark energy. That model is our best fit explanation. It accounts for the data, but it's a work in progress, refined by each new telescope survey, each new simulation. It paints a picture of a universe that's deeply structured, inherently in motion and still wonderfully mysterious. Our journey isn't toward a single hidden object. It's along the contours of an invisible geography. The cosmos isn't a static stage. It's a living, flowing entity. Our galaxy's movement through the dark, it's just one thread, part of a much larger tapestry. That invisible gravity pull we've been tracking, it shows a universe that's far more dynamic, more connected than what you see in a still night sky. That pull isn't a mistake in our science, it's a guidepost, a natural result. The cosmos has a hidden architecture, shaped over billions of years by dark matter. Etched permanently into how galaxies stream, every measurement of our speed, every map of the great flow, it's a reading of that hidden blueprint. We aren't being pulled toward some single, unseen monster. We're flowing with a gentle current, the cosmic web's current, sliding down a slope of shadow toward a gathering of light. We're on the brink now, a new era of discovery. Telescopes like Euclid and the Roman Space Telescope, they aren't just better cameras, they're gravitational cartographers, built to finally weigh the darkness. To measure how light distorts with breathtaking precision, the maps they'll make in the coming years, they'll transform the ghostly outlines in our theories into a sharp, three-dimensional portrait of where the pull really comes from. We might finally see the exact shape of the dipole repeller void, the full mass of the Shapley Supercluster. We might even find structures so vast, our current maps don't have names for them. When you look up, remember, we're all passengers on this voyage, our planet. Our sun, our spiral island of stars, all carried by forces on scales almost too large to comprehend, driven by a curiosity that's uniquely human. This journey through cosmic mysteries, it's still going. A story still being written in data and star